Morning. I was told to encourage you to go more to the middle, but I don't see anybody standing up, so I think we'll fine. I hope everybody make home back yesterday from Dublin and then got caught by the thunderstorm. And yeah, let's start this second day of the conference. So we're gonna talk about writing metal riffs using machine learning or ML.NET specifically, although we'll see about that. My name is Michał, and I really like to start my presentation with this picture from International Space Stations because it shows my two places I consider home right now. I come originally from northern Poland, but a few years ago I moved to Sweden to join this company. We're a Swedish-based consultancy. In the past we worked mostly with .NET clients, but now we do all-around things. And I think even Oslo caught up somewhere in that picture, just over the top, just behind the top. And yes, they give me this nice hoodie and they generally treat us well. But because we're gonna talk about metal music, I also have a appropriate T-shirt today. So I want to see my metal heads here. Hands up, who know what is this band? Good. It's, of course, Metallica. Picture from the 80s when they were still beautiful and young. And I'm going to pop up a few other bands during this presentation, so we're going to do this gas game maybe. But let's talk a bit about machine learning first. And it's just going to be a very quick jump into it. You've seen probably this many times, but just go through it. So basically, like to dumb things down, machine learning, in many cases, is about fitting model to data. And usually it's going to be simplified model. It's not going to be perfectly fine. You do it by just starting with some model, see how wrong you are, and then by making small adjustments, you get to the model that fits your data the best. And then use that model to predict the new values, which we call quite often inferring the new value. And sometimes this simple model is just enough, but sometimes you need a bit more complicated model, like this. And one way of getting more complicated model is, for example, neural networks. All right. What is this band? Hands up, who knows who they are? Okay, it's slightly less. This is Slayer. You even have like a hint on the top of the screen. All right. So when we had this linear function to like match to the model, we can describe it a bit by this formula. And two important parts is W and B, which are kind of describing the parameters of that function. And W, to simplify things, I'm really sorry to mathematicians here, is basically like how angled it is from the horizontal line. And B, which shows like how much shifted it is from the horizontal line. And those two parameters we call weights and bias. And we can visualize it in a slightly different way. We can visualize the function as a kind of a thing that takes W times B, W times X plus B.
Excuse me, can I try switching your adapter?
Yes, okay. I'm gonna switch adapter, so. Okay, doesn't bother me, so it's okay.
Yeah, we can try continuing.
Okay.
So,
All right. Sorry for that. So, as I said, we can describe linear function by those two parameters, and we can also visualize it slightly different. And our function can take more parameters, like this, because quite often in real life the things have more than one feature. Like classical example of you using like matching linear function to the data model is like predicting the price of an apartment. You have take like square meters and output the price. But we all know it doesn't. It's just the only feature that impacts the value of the apartment. You want to look into things as like, is it a new building or an old building? How far is from like a bus stop? How far is from school? So you're gonna have like a lot of features to describe apartment. And just to give an example, there's a data set quite often used for like, teaching people data science and machine learning with a set of like apartment in London. And this data set has around 400 features for each apartment. So you can have like a lot of, numbers and things describing apartment. But when we like add a few things to this calculation, first there's gonna do this calculation, but we also do something called activation function. We kind of have a neural network cell right now. And if we connect those cells into many cells, we can actually do very complex, like matching very complex models and do very complex functions. And and neural networks prove to be like very powerful model, but they also have some limitation. I just want to mention the talk that was yesterday by John. That was very like a good introduction from like from basics how those things look. I have to skim through this because that's not my focus. But if you're really interested how those things can be built ground up, like from simplest calculation up to like the full working neural network. This talk was fantastic, and just rewatch it after you go home because it was really good. But yeah, like neural networks have some limitations because they basically cannot keep state. So they take some model in and just output some, take some data in and output some data out. And they also are limited that they take the inputs must be the same length. So if you design the neural network to the like 100 integers, you always have like maybe sequence of 100 integers, or maybe not even sequence, but basically that's what you have to input. And if you make it to like classify things into like 10 classes, it's gonna always output 10 numbers. And if you just make it to be regression, it's gonna output one number, but that's just limited to what it can do. They have like, if you look at like a static architecture. But we have something called recurrent neural networks, which is basically you add another dimensions. So we have like copies of the same neural networks that pass data to each other. And this allows you to like, this allows us to do stuff with like sequential data. We can take input of sequences of multiple length and output one output. So for example, you take as a sequence comment like a commenter like a comment on the internet, and output is like a toxic comment or not. You can take just the one number and output many numbers, many like characters or whatever, and this is used for like sequence generation. You can do like sequence to sequence, so for example translation. There's like, this opens up a whole lot of problems that we can solve this way. But the basic recurrent neural network has problem that it has like fairly short memory. It's only like a one cell. And if you do like more of this, like you do longer memory for longer cells, you start having problems with like on like pure mathematical level. It's called like the problem of like exploding gradients on minimizing gradients. Again, we're not gonna dig into this, but this problem will solve that even more interesting neural networks called LSTMs, and this stands for like long short-term memory. And each cell has pretty much like a small neural network inside with like 4 cells that do something mathematically that allows you to keep state in a much more stable mathematically way. Again, very interesting neural networks. If you're really interested how recurrent neural networks work, Andrew Karpathy has a very good article on his blog about it. And in the style of Andrew Karpathy is just long with a lot of interesting things. Yeah, another recommendation to check and dig into deeper. So what the recurrent neural networks and LastTM specifically allows us to do is like doing cool stuff like writing a new Shakespeare play based on like his previous Shakespeare plays. So so I have opened from somebody doing this, and this text was written by a neural network algorithm, and may not always have sense, but you can see that, for example, it figure out like the structure you have when the place. Right? Like it figure out that I have to put something here that denotes that this is like beginning of a scene, and so on. So it's also very good to finding structure in text and building like innovating new text that keep the structure. So Andrew Karpathy has also interesting example of fake mathematical papers with algebra that was generated this way. And if you don't read into it, it looks completely legit. And if you like don't know nothing about mathematics, it probably just makes sense and you can impress people. But it's just gibberish. So it's just like a bullshit generator on the internet, just scaled up much higher. And another way we can do this way is generate music. So this is example of a guy who did like Final Fantasy inspired music. Can I play it here? Or maybe I cannot because SoundCloud. Where are you, SoundCloud? Yes, okay. How do I volume? Can we hear something? Headphones? Yes. So this music was generated by an algorithm. It at times sounds a bit weird, but generally it's like it's legit music. So that's cool. And oops, that's not what I wanted to show right now. Cool. All right, so we are in our Guess the Band. Hands up who knows which band it is. All right, good. What band is it? Yes. Great. Okay, so we've seen that like generating music with like piano music is like quite possible, and maybe it's because like piano is simple. And don't get me wrong, it's not hard to write piano, but piano you have like all the notes and it's kind of linear, and you have one note only at the one place. So basically, and you have just like in Western music we have like 8 notes that kind of repeat over time. So we have like octaves. So basically like sets of notes that go higher and higher. And in piano you have like one like C3 note is only in one place. So it's like fairly easy. Guitar, on the other hand, is slightly more complicated because we have basically like 6 pianos shifted by 5 notes. So I have this like E note here at like 6 strings fret 0, but also the same E is here, and the same E is here, and the same E is here, or actually, no, good. So we have like 3 octaves in guitar, so I think it's less than on piano. I have 5 or 6, or it probably depends. I have know nothing about piano, or not much. And those things kind of repeat, but they allow like you to build chords and so on. The thing is, like, because I'm a guitar player, I don't know nothing about this stuff on the top, those notes. Absolutely no idea. So we came up with another way to like tell us how to play music without knowing nothing about music theory. So this is something we call tablatures, and the the lowest note here on the pictures, also lowest note musically, but it's like highest note located on a guitar. So I think it like doesn't make sense because it's on the bottom here and it's on the top on the guitar, and it doesn't make sense until you put guitar here and you just look. Ah, so that's where I should play. And yes, so and the software I used, like Tablatures, and many people use, is called Guitar Pro. It's very nice because you can play those things and so on, and you can just slow them down and so on. And the good thing about it is like you have this like musical notation, but I said we don't really care about it, so let's just remove it for now. And okay. When I read into papers how people do this, like piano music prediction, they use notes, like the nose letters F or A on the B, and like in guitar it sort of makes sense, but that's not the only information you have, because as I said, the E3 note can be in like a few different places on the fretboard. So we want to like keep more information about actually where on the fret we play. So we actually have like two coordinates. We have like note, like a string, and then which fret we're playing. So yeah. Oh, I can also show you that like how does it work on guitar. That we can basically move notes around, and they're on a different place on the fretboard. But that's that's the same sound. So if I like turn back the notes again, I'm moving around, but the actual notes doesn't change. So yeah, it's also good to like this program is good to figure out actually how some music theory works. Although I haven't figured out much in 15 years, I never really needed this. Cool. So we talked about this a bit. We talked about neural networks. We talked a bit about how like guitarists like to read their music. So let's talk about ML.NET actually. So like now tying things together. And ML.NET is a fairly recent approach of Microsoft into machine learning, or actually fairly recent publicly, because it claimed this technology was used for years in PowerPoint and Excel and other products, just to give some like a smart features, some predictions and so on. But they had official release of 1.0 version, I think, in April, and this week they released another 1.1 version. And I think when I was writing the abstract for this presentation, they had version like 0.4 or something like that. They were basically making like a monthly releases. So let's go to a simple. Let's stay here. To a simple example of how things are done in ML.NET. So we have like most of API centered around pipeline. So basically write how we're gonna process our data. Yeah. People in the back, is it better? Hopefully, let's just go like 2 steps more. Okay, and so it's kind of mimic the process you do like within like the machine learning process, because quite often you have much more work to do, like cleaning the data and so on. And here also we're doing stuff with some data. We mark which is like a. I'm gonna maybe fire up the data. I'm using data sets for like taxi rides in New York here. So we have like input informations like how long it takes, how many kilometers, like a pickup location, dropout locations, and so on. And output is a price. So basically, we use it as we use that data to teach the algorithm to predict the price of the taxi ride. So we take our input columns, and we use something to use one-hot encoding, which is used for categorical data. So if, for example, let's say we have 3 categories in one input data for 3 colors, red, blue, and green. We give them 1, 2, and 3. And now the danger is like we give them those numbers because neural networks don't deal very well with strings, but they are really happy to deal with numbers. But the danger is when we give it numbers 1, 2, and 3, it'll try to figure out that maybe because the red got 2, it's twice as good as the green, for example. And because the blue has 3, it's maybe 3 times as good as blue. And we don't want machine learning to figure out those relationships. So we, instead of like one-hot encode it, so basically we create 3 features out of it. Is green, is red, and is blue, and it's going to have like 0 or 1. And that's called like one-hot encoding, and it's just used for this purpose, so we don't like kind of suggest that there is some like mathematical relationship between those things. So things like what kind of rate is, it was payment with cash, so we one-hot encode it. We indicate which are our features, so that's our input data. We also indicate what's our label, so it's kind of output data. And the whole kind of machine learning part is this line. Which kind of algorithm we're using. And we can use FAST3 for regression, or we can use another trainer. And I have, like, even if I no idea what algorithms are here, I can use our startnet.net approach, press dot and hope for the best. And you know, we can use like different algorithms, which I didn't even mean. It compiles in run and will predict stuff. I just know this one just works better in this case. So, you know, it allows you to use machine learning fairly productively in your .NET environment, and gives very good results. So, if I apart from this code, I have also like metrics on the whole data sets, and then we're actually predicting value for one example value. So we have like trip time that takes like 1200 seconds, a bit less, 3.75 mile, and we're gonna try to predict how much it takes. And it's probably gonna be really small letters in this window. And it shouldn't take so long. Come on. Yeah, so probably people in the back can see, but the actual fare of our data set was $15, and we predicted 15. So do you think, like, why do we know the right answer? And the thing is, like, quite often when you teach algorithms, you like take your input data sets and divide it into 2 sets. You have like learning sets and testing sets. And you do it for the purpose that we can test algorithm on data it hasn't seen. So let's say we have 1,000 rows of data. We take like 800 of them to train the algorithm, and then we test it on the 200, how it's going to work on the data it's never seen before. So basically, how it's going to generalize it. Because one of the problems, and quite common problems, like that our algorithm will like overfit the train data. And it's basically like similar to like you have questions to exam at a university and just learn those questions by heart. And then when you have like questions that is different but from the same problem area, you don't know how to act because you just memorize the questions. And that's like intuition about what overfitting is. So that way actually now running on the test data and see like how it works in the settings with the data I'd never seen before. So it's very good prediction. We have also some scoring numbers like R² and the root mean error that allows you now like to figure out how good of a model it is. And there's like a bunch of other metrics you can get with ML.NET. So it's quite nice. Another thing that's a good feature is actually AutoML. So we had to available like 6 or 7 algorithms here, but we don't have to do it manually. We can basically just write a code. We call it like experiment code that will run over all these algorithms. It found which fits the best the data set you have. This part of ML.NET is called AutoML. It's been released also with 1.0. I think it's in preview right now, but you can try using it. And it's also very interesting because now you just have to basically stand what is your problem. Like my problem is regression, so like predicting one number, or my problem is classification. So I want to say that this, for example, transaction is like fake transaction or good transaction. And if you know what kind of problem you're solving in machine learning, you can actually, run AutoML and be done. And right now, AutoML is available only for like regression and classification, but I know they're working on those things for other like sets of problems with machine learning. So I think it's also a very interesting development. So that's great. As I mentioned, I wrote this abstract like a few months ago for that presentation. And I quite often when I do with presentation, I just wrote some abstract when I promise ridiculous things, and I just pray they don't accept it. And I was unlucky that I actually accept this presentation. And it's this part itself is not so unlucky, but let's say that ML.NET isn't like maybe they had some things in the like roadmap, what's gonna happen, and not all those things happen. And like 3 weeks ago, I realized that deep neural networks are not part of the ML.NET yet. And that's problematic for solving the issue I promised in the abstract. But then I figured out that they do other things, because ML.NET can use pre-trained TensorFlow models. So I figured, so I can actually solve this problem in TensorFlow, save model, import this model into C#, and run it, and I have sort of solved it with ML.NET, right? All right, so we're gonna try this approach to solve our problem, which is we want to for a lost band of Metallica, just maybe help them write good riffs again. And we're gonna use this approach with TensorFlow. But first, guess the band. Hands up, who knows who are those guys? Great. Yes, great. Okay, so let's go to TensorFlow. And for TensorFlow, I'm using something called Jupyter Notebooks, and this allows you. Just go away. And Jupyter Notebook is a kind of like a software that allows you to run Python or a few other things in a browser. And I'm running it locally, but also like, for example, a lot of cloud providers have offer like Jupyter Notebooks with like with a backend of like machine that has like a very strong GPU and a lot of CPU. So it's like very useful to run like maybe heavy lifting of algorithms in the cloud, and you don't have to do it. And I do it locally. And TensorFlow is like Google's framework for dealing with machine learning with Python. And this year, like beta version of TensorFlow 2.0, which they do a lot of things to simplify API. They basically incorporated Keras into their own native API. Keras was kind of like a high-level framework over TensorFlow that allowed you to like think more into like more higher-level abstract. You don't have to declare like a network on the like each neuron level. You're more just like I want to dense neural network. I want to LSTM with these sizes and so on. So allow you to do things much more efficiently. So here we're doing some stuff about. Oh, maybe let's look at the data I prepared for this because it's also interesting. I took let's just minimize that for a moment. Yeah. So I took some. I took basically two first albums of Metallica and cut those songs into kind of like a riffs, like kind of repetitive sequences of music that I used, and I have created a lot of them, around 60. And it seems like not a big data set, but if we, the way we do it, like all those riffs has around like 50 to 100 notes, and I cut them into sequences of 30. So if you have like a 50 notes, you can do like basically 20 sequences out of it, because starting at 0, starting at 1, and so on. So just kind of moving sequence. And we use these sequences, like I take 29 first 9 notes of this sequence to see like, wow, those 29 notes were previously, and to predict what's going to be a 30th note in that sequence. So I generated around 1,200 sequences in effect. And it's very interesting how actually guitar profiles are constructed. We can look into this, because it was part of solving the problem. Data. So guitar profiles are basically like a zip file that when you unzip, they have some things in it, there's content, and there's like a big XML file. Internet Explorer. Oh, I guess if we talk about 80s metal, it's appropriate to have Internet Explorer also. And basically like describe this in like very convoluted way. Like this structure completely doesn't make sense for me. Took me some time to figure out. So I get, okay, I'm gonna move it to a bit structure that's more friendly for me. So yeah, I have a converter, and I basically end up in a structure more like that I have a track, which is the song, like speed and time, but I end up not using it for training the algorithm. So it's just like I generate the sequence of notes, and then we can probably see like this is gonna work better if it's a faster music or slower. And we can divide music into bars, and bars are those kind of segments of music. And each bar will have like some amount of chords, and chord have one or two notes. I wrote it because like in a guitar you can like, play basically few notes together, and they sometimes make sense, sometimes not. But they build up a chords, and probably like the most popular in music chord is called like power chords, because they sound powerful. You basically get like a one note on one strings, and the two next strings you have like fret two frets ahead. So 5 7 7, 1 3 3, 0 2 2. And if you know this, how to play, you pretty much can play like a whole grunge music. So you know enough to. All right. That was a bit rough comment. I'm sorry for that. I really like grunge music also, but it's just musically it's maybe not so complicated. Cool. So basically, I just converted this structure that was like weird and whatever into something that makes more sense for me. And actually, for the input to sequences, I figured out, okay, what's the good way to represent that? And I see in some like articles that people did like F and then 0.25 to note that it's a quarter note, because notes can have also different lengths. So if we have like a full note, it's basically, oops, that was a bad sound at this time of the day. So it's gonna be a very long note that's gonna fill the full bar, but you can have like a half note, and then you can fit two notes into the bar. You can have a quarter note, and then, you know, they feel like something doesn't add up. Oh, it's too much notes right now in the bar. Because I have, okay. Yeah, so now I have 2 quarter notes and 1 half note. So length is also important. And quite often in metal we have like a lot of 8 notes. But, or triplets of 8 notes even. But yeah, I'm getting too much into musical stuff, and that's not important. But I just figured out, okay, so I'm gonna represent it by kind of like I'm gonna have like number of string dot number of frets. So it's gonna be like this sounds, it's gonna be 0.5. And if I have like more like notes in a chord, I'm gonna also smash them together. So this will be represented like 0.5 underscored 1.7 underscored 2.7, and they're underscored and length of that note. So it's gonna be this is 8 note. Remember? Yeah, so it's gonna be 0.125. So this is gonna be basically how I'm gonna represent music. So I run this code here to convert the music, and I generate output out of those files, which is gonna be input into my neural network. So here's my output file. And you can also see this like it's probably not very well visible. I just use basically like I think it's called pipe, and I have to just like divide the bars into it. So it has input data, and we'll see if we'll able to predict also that, you know, those bars make sense, and maybe put like full note or just like eight notes into the bar. So basically like making the sense of like the structure of the music also. Okay, so let's get back to our Python code. And yeah, we do some like importing stuff. So basically what packages we're gonna use. And now I'm gonna use the data file to read it. You can see it has like 45,000 characters. So each, so one character is around like 5 or 6 characters is a note. So probably there's like a 10 or 9,000 nodes there in this input data. And yeah, we basically do things. And now I generate those sequences of length 30, as I said. It's something we can think, but basically like take all those input data and generate it into like sequence of length 30, and I treat like 29 is like inputs, like how many nodes, and the 30 nodes will be predicted by the algorithm. And then I build our network, and that's how you construct like neural networks in Keras. You basically like add layers, how it's gonna look. So I have one LSTM network. The LSTM is something I briefly mentioned, like those recurrent neural networks that are very good to generation of data. Then we have a dropout layer, and dropout layer is a very interesting thing. Like when I read about it and think, that does it really work? Because it doesn't make sense. Because what dropout does it's like randomly remove and disperse 30% of the nodes in the network. So basically, it cuts off pieces of network, and it actually makes the network train better. And you know, you just kind of remove pieces of your algorithm to work better. And what it forces us to do to network to find a lot of different connections to solve a different problem, because like you disable part of the networks every time in every kind of iteration, and it's forced to find a different connection as well, and it's this way able to generalize the problem more. So it's like one of the mechanisms used against overfitting of the algorithm. And we run another LSTM. Dense is a kind of neural network I showed you at the beginning that every node connects to every node. And at the end we enter a number of nodes. So this is kind of sequence we want to return. We can use like model summary in Keras to describe like visually the layers of the network. And it also shows like a shape of the data if you need it, and how many parameters it takes. So it's just good to like maybe double check visually how's your argument doesn't make sense. And there's actual training. And I'm not gonna run it on this data set because on this computer it's gonna take like half hour and increase the temperature in this room. But I ran it yesterday evening last time, and good thing when you see it, like we run epochs or iteration. I decided on 2, and we calculate the loss. And if you remember, there's like early chart I saw with like kind of red bars going from where data set to initial data. So loss is like how bad we are with like our prediction. And initially we started with pretty high loss, but I can say with each iteration was like going slowly down up until around 0.1, I think. So I guess looks like not much happened since iteration 168, but that's something like that. Like when you train things for over a time, at some point you're gonna reach the moment it's not gonna do any better. You're not gonna have more benefits of training more. So quite often it's beneficial when you train algorithms to just kind of chart the loss, and when you see and you kind of flat out, then you're probably not gonna get much more out of network. If you see it flat out and goes up, then you're in a problem because then your gradients are escaping and it's you start overfitting stuff. And that's the code I used to save the model. So we're gonna use it in C# code, and cool. Let's try use it in C# code. And I think that's where this presentation starts to like kind of go off the rails, because things. It was beginning of this week when I realized that things may not work so well. So I was afraid that now set up start project. What's gonna happen that my presentation will like share the fate of metal music in the 90s. So yeah, I loaded TensorFlow model from a path and so on. I experimented in many ways how to do it, and I just run it, happy that it's gonna work. And yeah, it's just not working, and I couldn't figure out how to make it work. It works on examples that ML.NET shows on like recurrent neural network, convolutive neural networks that you use for like image recognition, but I just couldn't make it work in this example. And I was like, okay, I have like 2 days to presentation. What should I do? And I figured out, okay, there's another way to do it. There's a format called ONNX, and it's just kind of like a formal, like a common model that a lot of framework use to share a trained model. And I said, okay, ML.NET technically takes ONNX. I'm not sure if it's gonna work, but I think it does. TensorFlow officially doesn't support ONNX, but there's like way to make it run. But then I run a TensorFlow 2.0 version beta, and thinks those library doesn't work very well with it. So I couldn't exploit to NNX, and just like couldn't make it work this way. So I promised we're gonna work with ML.NET, and it's not gonna work with ML.NET today. Yeah, so that's not great. But since we're already there, I trained this network with TensorFlow, so we might as well try to generate some metal music with TensorFlow. So let's just continue with it. And yeah, so this is basically like a prediction node. And what I do here, like let's say we want to generate 50 nodes. So for like, I start with some random sequence, and the way I do random sequence, like from all the input data I have, I just pick like random, I think 30 or 50 characters, and it's gonna be like my input set, because the recurrent network needs some input. We have to start with some data to generate new data. So we could start with some like music written by myself. But I just like take like random piece of stuff from my input set and then try generate music out of it. So now when I run this code, we actually output nodes. So you can see like 0.2 is like 0 string, 2nd fret, 8th note. 0 string, 5th fret, 16 note, and so on. Only generate music, and I can see like actually figure out that they have to be bars every now and then. So that's good. And if we count music, so it's like 8, 16, 8, 8, 16. So we have like quarter. 2, 3, 4, 5. So actually fit 7 eighths into the figure. So it wasn't perfect, but actually figure out that around the amount of notes it need to fit into thing. And so yesterday evening I actually got it finally working, and so just in time. And I don't have like an automatic translation from this notation to Guitar Pro, which would be nice to show that it works. But I took the stuff I generated yesterday and just rewrote it. Just gonna remove those because it doesn't, just to show you that this. It's not like all right. It's like three. It's lacking like 1/8 note here, one I think quarter note here. This is also lacking like a 1/8 note, but this is okay. Like it worked out how many notes put in here. Again here, and also this makes sense. Like figure out those power chords from the structure we have. And also, it actually, all the notes here are from like a pentatonic scale, which is like a common scale used like in blues and rock. So, oh damn, I actually admitted I know something about music. So, yeah. So, I'm gonna play this. So, it's not maybe a great piece of music, but it has some nice parts. And it's, if you play it with enough overdrive, could be actually qualified as metal. So that was very successful, I'd say. I think that's about the demos. I think maybe I have a few more slides to show, and then we can take some questions. And maybe have some fun also. All right. So some future work. I would like really this TensorFlow to ML working. Right now, on the roadmap of ML.Node, that's the approach they want to take. They want to allow you to use other frameworks to like define deep neural networks, but somewhere along the line we'll also introduce to ML.NET. It's probably not going to be super quickly, but they're thinking about working on this. Another option in like .NET space for you to try if you want to like kind of something like TensorFlow is Cognitive Toolkit or CNTK. This is like a Microsoft framework for running neural or like deep learning algorithms, and you define things kind of similar way than in TensorFlow. It used to be only Python, which Microsoft got a lot of crap from the community, but they're making like a machine learning thing that's like not in C#. So they opened API in C#, and like few months ago when I look at it, like the C# API didn't support all the features, but it's quite getting there. So you could start getting dangerous with it. Another thing I want to do is write back conversion from like the note notation I did back to like Guitar Pro. So you can actually like for the demo it would be nice to run these things we generated here to show they actually work. Probably experiment with few network architecture because you can. I had those like kind of numbers that I came from somewhere that like I'm gonna have 256 here and 512 there. And a lot of about machine learning is experimentation. You see like what networks work or not, and you just train a few models. So we would test on few models how they would work. And something that just happened just before the conference. Oh yeah, more data. I'll probably just would like to also some Slyer or Pantera on Anthrax to train that to give like maybe more diverse music. And and this happened before the conference. Like Martin tweeted, "Can I use Rockstarlang?" Which is kind of like something like a language that Dylan BT architected, that you use kind of lyrics from the 80s music to generate code. And it'd be really funny to use like lyrics from 80s music to generate 80s music that maybe work together. And actually, Dylan has a plan to organize like a competition for like Rockstar developers to generate kind of like song and something cool, and takes like maybe 8 or 10 of those posts and record album out of those, like with rock music. But also we can check like a Rockstar Lang today and write some code and became certified Rockstar developer. I think Dylan is on the conference, has a stickers for certified Rockstar developers, so you can become just this and put it on your LinkedIn. It's gonna work fantastic. All right, one more band for today. This is great hair. Do you know who are those guys? Yes, great. All right, that's all I have for today. I'll take questions.
Yeah, maybe I misunderstood, but you said something when you were trying to load your model into ML.NET. You
Yeah.
said that it was working for CNN, not for RNNs. Was that right? Or
Yeah, so it's more like it works. Of course, an example that Microsoft have for this, and I couldn't make it work on my example. So when you go to there is a GitHub repo of machine learning examples where Microsoft prepare basically like sample codes how to use ML.NET with different scenarios. And they have like an image classification using TensorFlow here. So that's the example I will try to build on, but unfortunately I didn't manage to make it work. I think it's possible, I'm just missing something, but just couldn't figure out in the time I had for this.
What tool would you recommend using to tune parameters to get an optimal result? Say you've got some input parameters you want to predict what parameters to use to obtain
Yeah.
an optimal result.
So the question is, what tool would I use to tune parameters? You mean like hyperparameters of the network, or?
Just could be some tuning parameters, for example, to get an optimal output, which could be optimal energy use, optimal price, whatever.
Well, look, a lot of work with working with machine learning is actually a bit of experimentation. Like after a time, you get more intuition, like which kind of network architecture will work for this this problem you have. And I'm not sure if there are like an automated solution to kind of figure it out for you at this point. But there's a lot of happening in this space, and I think there's definitely somebody working with it. And like the AutoML is one example of just one way to just have automatic approach, but it's at this point quite limited yet. Yes?
I've used Accord.NET. Can I say something about how ML.NET is compared to Accord.NET?
Yeah. So the question is, have I used Accord.NET, and can I say something about it? So Accord.NET is it's a, let's say, pretty old .NET framework, but they recently open sourced it. So like at some point I thought it's maybe like not live anymore, but it's probably gonna bring a lot of life. And Accord.NET has a lot of algorithms built in for a lot of like statistical methods. It's very good for like signal processing, for vision processing. So it's also one way to look into if you're like in the .NET space to use things. And I haven't used it much. It's kind of like, I see like the approach is different. Like here they tell you like, oh, maybe you want to use multiple linear regression, L2 regularization with L2 loss. And ML.NET is more approach, this is the problem I'd like to solve, and how to figure out. So I think like the target is if you're like a bit more statistician or mathematician, you know exactly what to want to use. then Accord.NET has a lot of those methods implemented. And ML.NET is more like approach has like I'm a developer, I just want to like predict, you know, the price of something, or I want to classify I don't know, like my customers to like few buckets and so on. And I think that's kind of like the target is slightly different, who those frameworks are targeted for. Any more questions? Yes?
So you ended up with some of the bars lacking a note or two.
Yeah.
But what about your training data? Could it be that some of it was in 7/8 or something like that?
Some things were like 6/8 and so on. So I think that could impact part of it. But I think what impacted it most, I had like some, like, you know, quite often like you play a chord, for example, and just go over long. So basically like those notes overlap to another bar, and I didn't implement support for this. I didn't implement support for like pause notes or quiet notes or like muted notes. So I think some of those could actually impact this and cause this. So that's, you know, another things that maybe I could implement. Other things, there's like a lot of technique with guitar, like you bend strings or just like, you know, do tapping and so on. And those things are like kind of marked in these tablatures, but I absolutely ignore this data right now. But could probably use it to, you know, also, you know, just predict, and maybe actually predicts also solos in the future. So like more complicated structures musically. All right, if there are no more question, I'll also be around for the 2 next days of the conference. Feel free to come and talk to me. And thank you for coming so early, and enjoy the rest of the day and the conference. Thank you very much.